Hello everyone, today I am going to show you how you can utilize such a Peltier module to make your own personal mug cooler. You can have a nice cold water with this mug cooler, and price of this kind of module came down a lot with time. Now you can get such a Peltier module at a good price, and with this kind of module you always need a very good heatsink to make such type of cooler. And as you know, that CPU cooler has become more and more prevalent, and you can get a fantastic looking heatsink or CPU cooler at a good price, which you can use it as a heatsink. I have one at my disposal I used, and the heatsink, you can see it has also a fan, and the price is only $20. So this video has two parts. The first part tells in simple way how you can make such a cooler, and the second part has an in-depth analysis to what extent the cooling can go and how long it will take to cool down a full glass full of water. Many years ago, a person named Peltier did an interesting experiment. He joined two dissimilar metals, bismuth and copper, like this, and added a voltage source in the circuit. He found one junction colder than the ambient and other hotter. After many years, with the advancement of solid-state physics, we now know that it's all about electrons' energy. The free electrons in bismuth are lower than those of copper when crossing from bismuth to copper. Electrons absorb extra energy from the environment, and the temperature gets lower at that junction. In the other junction, exactly opposite is going on. High energy electrons lose extra energy, and that comes as a heat. Peltier effect is more intense in metal semiconductor junction. If a metal comes in contact with an N-type semiconductor, the energy gap between the metal and the semiconductor is higher than metal-metal junctions. Therefore, the cooling effect becomes more intense. Usually, in Peltier modules, bismuth telluride is used as semiconductor. Different types of doping are used to make N-type and P-type. With such a metal semiconductor junction device, the lower side gets cooler and the upper side gets warmer. In a Peltier module, large number of such elements are connected in series to absorb more heat, and both sides are covered with ceramic plates for electrical isolation, and all sides are filled with sealant. The amount of heat absorbed by the cold side can be expressed by this equation. Qc is the cooling power, S is the Seebeck coefficient, R is the internal resistance, and K is the thermal conductivity between the cold and the hot side. The cooling effect expressed by this first part of the equation shows a linear relationship with current. The middle part is purely Joule heating, and half of this goes to the cold side and half to the hot side. The third part tells how much heat flows back to the cold side from the hot side. Again, back to the equation, you can see only the first part contributes to the cooling and linearly increases with current. The Joule heating, the second part, is quadratic, and as you can see, it's low initially but increases rapidly with increasing current. If we consider only these two effects, we can see there is an optimum value for the current. where the cooling effect is maximum. Now let us consider the third term. So to get better cooling, we have to take heat away from the hot side. That is why we need a good heatsink on the hot side. Depending on the heat sinking power, the optimum current goes down to some extent. So initially it was here with a very good heatsink or 100% heat sinking, and it goes down a little. I bought some Peltier modules from Amazon. The model number is TEC 1712705. The manufacturer's data is shown here. Maximum cooling is 49 watt. We'll consider the 50 degrees centigrade values, and the maximum temperature difference can be created is 75 degrees centigrade. Maximum current is 5.3 amp, maximum voltage 16.2 volt, and module resistance or internal resistance is 2.75 ohms. As the module has maximum current of 5.3 amp, for any cooler we have to use less than this value. Here it shows the basic guidelines for using a Peltier module. First is the application. What kind of heat load we are going to use. In my case, a small copper mug. I need to cool a mug full of water. Then comes what kind of heat sink we are using to remove the heat. And the third is the type of module we are going to use. Depending on all this, there should be an optimum current to get the maximum cooling power. Empirically, we can start half of this maximum current of the module, like 2.5 amp. We can then increase or decrease the current to get the optimum value. This slide shows the schematic diagram of the mug cooler. On the hot side, an air-cooled heatsink is attached. On the top side, a 5 mm thick and 4.4 cm aluminum plate is used, which is in good thermal contact with the cold side using thermal paste. The aluminum plate serves two purposes, as there is thermal insulation above the heatsink. The cold side is exposing its surface out of the insulating barrier, and the weight of this plate maintains a pressure on the contact paste between the cold side of the Peltier module and this plate. On top of this plate, the copper mug is placed with water inside. A variable power supply of 5 ampere maximum current is used to deliver the power to the Peltier module. The essential part of the cooler is a heatsink. I bought this fantastic looking heatsink from Amazon. This type of heatsink is basically used with CPU cooler, but I am using this to take away heat from the hot side of the Peltier module. Two aluminum extrusion poles are used to mount the heatsink on a wooden base. I used a small wall mount 12 volt power supply to drive the fan of the heatsink. It is a low power fan. You can see it has a 4 pin. It has 4 pin. Pin 1 is negative, pin 2 is 12 volt positive, pin 3 is not used. Pin 4 needs 3.3 volt to activate the fan. I use this small circuit consisting of two LEDs and one 3.3 kilo ohm resistor on a proto board. All other parts are shown. A plexiglass with a square cut hole serves as a thermal insulation, the aluminum block, and several M4 and N5 screws and two standoffs. Peltier module is placed on the heatsink and the copper mug is placed on top of the aluminum plate. A power supply is connected to the Peltier module and its voltage is varied to maintain a different current level. A thermocouple reader is used to measure the water temperature. After connecting the fan and the Peltier module with the power supply, fill the mug with 100 milliliter of water, keeping the voltage setting low, and slowly increase the Peltier voltage and monitor the current. Set the current at 2.5 amp and measure the water temperature after nearly 40 minutes. The minimum temperature is stabilized. Record this temperature. Increase or decrease the current at various levels and record the minimum temperature. After nearly 40 minutes or an hour, temperature is stabilized. At the minimum level, the data is shown for different current levels. For 3 to 3.5 amp, minimum temperature is achieved, and that is nearly 4 degrees centigrade. This is the type of heatsink that I'm going to use. It's a CPU cooler, and this is the terminal connected to the fan, and on this part, the shiny part, the module will be placed. This is the module I'm going to use, and it has two terminals connected to the terminal block. I'm going to use some thermal paste for each thermal contact. Using a brush, we have to apply the thermal paste, and this is a kind of insulation that needs to be used between the heatsink and the Peltier module. Thermal paste is being applied. To cover the entire contact surface. A very thin layer is good enough. The module has a hot side, so the hot side will go to onto the bottom top of the heatsink surface. And the insulation is attached. Thermal paste will be applied again on top of that cold surface. And there is a tiny gap that should be sealed with some kind of sealant. Silicone sealant is good enough, so that heat from the bottom doesn't go onto the top. This aluminum plate now will be placed on top of this Peltier module, and it has to be pressed a little. The two terminals will be connected to the supply. Now the mug is on top. A thermocouple is attached to measure the temperature. The room temperature was 25 degrees centigrade when it was tested. Current was kind of set to close to 3 amp. And as you can see, with time goes on, the temperature is going down. And if allowed sufficient time, like 30-40 minutes, it will reach the minimum. Now after some time, the temperature goes down to 17 degrees from initial 24. Now it is 11 degrees after some time. We get minimum of 5 degrees after 30 or 35 minutes. So you can see some condensation on the mug because of the temperature colder than the room temperature. Some moisture is deposited, you can see. This part of the video will enable us to predict the optimum current for maximum cooling. How long will it take to cool the water, and if the water quantity is changed, what would be the effect? We will do some simple calculations with the electrical parameters of the Peltier module, and we will consider thermal properties of the Peltier module, the heatsink, the mug, and the contact materials. We will convert the thermal quantities into electrical quantities and use circuit simulation software LTSpice to analyze the behavior. We can also use Python code instead of circuit simulation software to get the results. We must determine the thermal resistance of the copper mug that I used. I will calculate the thermal resistance of the aluminum plate underneath the copper mug. Thermal resistance and Seebeck coefficient will be calculated from the manufacturer's data for the Peltier module. And I'll use the manufacturer's data of the thermal resistance for the heatsink, which is 0.25 Kelvin per watt. Manufacturer's data of the Peltier module is shown here. We will use 50 degree centigrade data for our calculations. We will need the value of electrical resistance, which is already given here, 2.75 ohm. We will calculate the Seebeck coefficient using the equation Vm by Th, which is 0.05 volt per Kelvin. We can calculate the thermal conductance, or K, using this formula, and that is 0.52 watt per Kelvin. And from this conductance, we can get the thermal resistance, which is 1.933 Kelvin per watt. To analyze the behavior of the cooler using a circuit simulation software called LTSpice or any other which you like, we need to convert the thermal parameters into electrical equivalents. For instance, heat is equivalent to current, temperature, voltage, and thermal resistance is electrical resistance. So the heat, the quantity is watt, and which is equivalent to current, that is ampere. Temperature in Kelvin, which is equivalent to voltage V, and thermal resistance theta, which is equivalent to resistance R. After getting all the parameters in terms of electrical quantities, we can use this circuit. Let me explain a little. This section shows the electrical part of the Peltier module consisting of the power supply, the internal resistance of 2.75 ohm, and the Seebeck voltage, which depends on the Seebeck coefficient and the temperature difference between the cold and the hot side. The upper section represents the thermal part of the cooling system. Some of the parameters we already know: the thermal resistance of Peltier module, the internal resistance of the Peltier module, and the heatsink is 0.25 Kelvin per watt, and we know the Seebeck coefficient. We can find the cooling effect, and the electrical resistance we already know. The only unknown will be the thermal resistance of the copper mug. To determine the thermal resistance of the mug, I used 4 resistors, each of a value of 10 ohm. These are connected in series and attached on the bottom of the mug as shown. A thermocouple is also attached on one side of the mug to measure the temperature. The resistors were powered with a power supply of and 33.6 watt was delivered. Temperature of the mug was rising and then stabilizes after some time. Recording the final temperature and subtracting from the room temperature, we can find out the temperature difference, delta T. The temperature difference was 43 degrees centigrade. Dividing this value with the power delivered, we can get the thermal resistance of 1.28 centigrade per watt. We also need thermal capacitance later to determine how long it will take to cool the mug water. We will use these capacitance values later. Here is the complete electrical and thermal parameters of our system. Considering the non-ideal contact of the bottom of the mug on top of the aluminum plate, we can consider the thermal resistance of the mug to be approximately 1.5 degrees centigrade per watt. We can use all these parameters, draw the diagram and simulate using LTSpice. Here is the simulation result. As the current through the Peltier module starts increasing, the mug temperature starts going down. At around 3.6 amp, the minimum temperature of 3 degrees centigrade is reached. If the current goes further higher, the temperature goes up again. So the optimum value should be around here. Instead of LTSpice, one can also use Python code to analyze the cooling effect. The Python code that I used is shown here. And I got similar kind of results using the Python code. So far, we analyzed how low the temperature can be achieved with our cooling system. However, I have not discussed anything about how long it will take to reach the minimum temperature. With our common sense, we understand that if we take a little amount of water, it will be quicker to get the cooling done. But if the mug is full of water, it will take a longer time. Here comes the concept of heat capacity. Before going into that, let us look at this simple circuit. Consisting of a voltage divider and a capacitor. If there are no capacitor in the circuit, the voltage will jump to plus 5 volt in no time. However, if the capacitor is used, whenever we connect this supply, it will take some time to reach close to 5 volt. Higher the capacitance, longer the time it takes. Here is the modified electrical equivalent circuit considering the effect of heat capacity. The capacitor C1 represents the heat capacity of the mug filled with 100 milliliter of water. For full 350 milliliter of water, the value will go higher. Here is the simulation result considering the heat capacity. It appears that for 100 milliliter of water, it will take nearly 30 minutes to achieve minimum temperature.